Good day and a warm welcome on behalf of NTI Audio. Let us imagine you are in a studio or maybe in a concert hall and you want to determine the behavior, the characteristic of an audio instrument or of an installation, whatever. So for that purpose, you need a simple, proven method to measure the frequency response. And this is actually the topic that we are covering in today's webinar. My name is Markus Becker. I'm moderating this presentation and I'm assisted by our product manager, Greg Schmiedle. He is taking care of the incoming questions and comments. On the left-hand side, you see the topics that we have prepared for today's webinar. We start with a brief summary on why we are talking about this solution. We will then introduce you into the available methods or principles to measure the frequency response in a quick and easy way. We will then dig a little bit deeper into the comparison of classic pink noise versus cyclic pink noise. Then we have prepared a practical presentation for you in two parts, where we will show you the key features and procedures to execute such a measurement. After that, I will summarize the procedure how to define a tolerance band for a pass-fail test. I will then follow up with a summary of the key topics and add some more hints and tips. I expect that this presentation will last a little bit less than half an hour. Well, coming back to the situation that I described initially, if you are expected to execute some typical tests of an audio device or a system, this could be, for instance, necessary because you have to characterize the device, or maybe you have to look for an error, for a flaw and identify it, solve it, or you have to fine-tune your system. In all these cases, you would typically execute certain measurements. One of them could be, for instance, to measure the noise floor coming from the device. Maybe there is some hum. Maybe you want to determine the distortion. So to answer the question whether how pure the input signal is replayed by your device. But the most important characteristic you're most probably looking for is the frequency response. How accurate does your device or does your installation replay the input signal? And this is the topic of today's presentation. So there are basically two principles, two methods how you can determine in a quick and easy way the frequency response. One is by using a sweep. Can be a step sweep, can be a glide sweep. In other words, you have a sine tone that you of which the frequency you're increasing or decreasing depending what you prefer over the frequency band, and you measure the level at different frequencies over the frequency band in order to determine the frequency response. A second approach, different approach, would be by using pink noise. So you replay pink noise and you measure the spectrum that is coming out of your device or your installation. The cyclic, or we call it fast pink noise, basically does the same as the conventional pink noise. I will show you the differences just in a second. But getting back to the sweep approach, what are the pros and cons? First of all, it is a very fast method. It's very precise. Furthermore, it allows you to acquire several measurement results in just one cycle. So that means not only the frequency response, but also the distortion, maybe other parameters. So that is really very powerful. On the other side, keep in mind, for this measurement, you need to synchronize the generator and the analyzer in an appropriate way. Typically, you do that in the same instrument. But this is a certain challenge you have to cope with. And another possible infringement would be that this test might be affected by certain signal processing devices, like, for instance, a feedback suppressor. Doesn't has to be, but this could be a reason for not using the sweep approach. Here in this webinar, we will focus on the pink noise approach. And as stated before, we have this test signal, the pink noise. I just choose the color pink to make it clear. Of course, the signal itself has no color. And we are measuring the spectrum over the logarithmic frequency axis. And in an ideal case with a perfectly flat frequency response, you would expect a measurement result like this one, regardless whether you're using a conventional pink noise or this cyclic or fast pink noise. So the advantage of the pink noise approach is it's, again, a very precise method. The test signal is widely available. There are lots of signal generators on the market that can create pink noise. On the flip side, however, it's a very slow measurement method. You're going to see that also in our practical presentation. So coming back to the initial challenge, you don't have much time, you want to be fast, and in that case, the solution would be this cyclic or fast pink noise, because it is very fast, very quick, it is still precise, it is simple to implement, it is a solid and proven method. The backdraw is you need a special test signal, so you need a device that can replay this special test signal, and you must make sure that the analyzing unit applies the same sampling period than the length of this fast pink noise. You're going to understand that just on the next slide what that means. So let us take a closer look on these two different noise signals, the classic pink noise and the cyclic pink noise. Classic pink noise is, in theory at least, a complete random signal, which means it has infinite periodicity. You will never meet, in theory or in an ideal case, a section of this pink noise that is being repeated over time. However, on the other side, when we look at the cyclic pink noise, this is one of the core characteristics of this signal. It is a deterministic signal, so not random, and it has a defined periodicity. What does it mean? If we look here at this graph and on this time plot, you see here we have a certain segment of pink noise signal, and that is being repeated over and over again. It is, we call it, stitched together seamlessly, so there is no interrupt in between these blocks. Each block has the same duration, t, the period length, and so it's being repeated again and again. Eventually, it has the same or very similar characteristics like this conventional pink noise, but it has some advantages. A real-world pink noise generator typically has a periodicity, so that it's almost impossible to design or create an ideal pink noise generator. In reality, they have a periodicity, typically 20 seconds or longer. On the cyclic pink noise, as stated before, we by default have a periodicity, for instance, 1 second or 4 seconds, if we refer to the test signals that we and TI Audio are providing. In both cases, the spectrum of the signal can be characterized by a constant energy content per equidistant logarithmic frequency band. That sounds a little bit cumbersome. What I want to say is, if you look at the 1/3 octave, any 1/3 octave or any octave band in your spectrum, it will always have the same energy content, and this applies for both signals. This is the core characteristic of pink noise. If we want to measure by using a pink noise signal, an ideal pink noise signal, or let's say a realistic classical pink noise signal, we need to wait for typically 20 seconds or longer until we have stable and reproducible results. If we do the same with the cyclic pink noise, however, we can do it much quicker. We only need 1 or 4 seconds. So this is a key advantage of this approach. So that brings us already to the practical presentation. I have prepared 2 setups here. The first one is feeding the output signal from the EMMA Pro to a mixing console. and the output of the mixing console to the input of my XL2 analyzer. Both devices are connected via USB to my PC, and here on my PC I have two software packages that allow you to watch the screen content of the EMMA Pro and of the XL2. In the second part of my practical presentation, I will replace the mixing console by a TalkBox in order to execute an acoustic test. So in addition, I will also connect the XL2 to a microphone so that I can pick up this acoustic signal from the TalkBox for my measurement. Okay, let me show you the screen content of these two devices. On the left-hand side, the EMMA Pro, on the right-hand side, the XL2. And you see here on the left-hand side, I have right now activated the classic pink noise signal. And I'm measuring here on the right-hand side with the XL2 in the live mode. So this is the instantaneous signal that is coming from the EMMA Pro through the mixing console to the XL2. And I think you already see it. We have a pretty unstable result. It's going up and down, flickering, especially the bands here in the low frequency range. It's virtually impossible to determine a stable result here in this range. And this is, of course, not very satisfactory. So what can I do? Of course, I could say, well, I go away from the live level and I switch over to, let's say, LEQ. This kind of averaging measurement that is available. And I start the measurement. Now you see it takes a little bit of time, but over time the screen, the spectrum becomes more and more stable, and eventually I am achieving a situation where I could say, yeah, now I can really read out my device. Unfortunately, I have one backdraw, because as soon as I change, for instance, the setting for the low frequency band here on my mixing console, it reacts after a while, at least when I'm increasing the level. But if I do the opposite, if I go down with my level again, then it takes awfully long time until this LEQ adapts to the new status. So this is really very tiring. It's not really usable in practice. It just takes too long. So this is not really a good solution either. So I'm going to stop this measurement. I'm going to show you what does it mean to use a fast pink noise. So first, I switch here on my EMMA Pro from pink noise over to file. And here you see file. I have under signals this fast pink 1 test signal available. And on the XL2, I go away from the EQ, the LEQ measurement, and I go over to the EQ 1 second measurement. This is the corresponding measurement that allows me to analyze the signal here on my XL2. Now, what I need to do is to adjust the level of my EMMA Pro a little bit so that we are more here in the middle of the screen. See it here. Now here you see now the characteristic of my mixing console, very easily, very stable. And if I now change the settings of my equalizer, the low band, going up, going down, mid-range, the reaction is immediate. So it's extremely comfortable. Even the high band, of course, whatever you do, you get a very quick, very immediate and stable response, which allows you to determine the characteristic of your device. By the way, I have chosen the 3rd octave resolution, which is a kind of a standard. You will see that I can inform you that if you use, for instance, the fast pink 4-second signal, you could even increase the resolution to 1/6 or 1/12 octave. But let's stick to the 1/3 here. Now, the second part of my presentation is replacing the mixing console by the TalkBox. So I connect the EMMA Pro. I mute it for a second. I connect the EMMA Pro to the TalkBox and the XL2 to the microphone. By the way, if you look on the right bottom corner of your screen, here we have the TalkBox, and in front of that we have the microphone that I have now connected to my XL2. So I just need to adjust the scaling a little bit. and also the level of the EMMA Pro output. Okay, now I will unmute the EMMA Pro and you will see the spectrum coming out of the talk box. Maybe you can hear it in the background. This is this fast pink 1 second, fast pink noise. And this is the corresponding spectrum. Now, let's assume that you want to do a passed-failed test, which means you need to save a reference curve, which is your golden sample, where you know this is the good behavior. And then you want to compare it against the next device. For that purpose, we click here on this icon and we capture the current spectrum. We assign it to a memory location. I choose just the C1. I could rename it, which I will not do right now. And now I have saved it on the XL2. And in the next step, I will start the so-called tolerance mode. For this, I have to select a previously saved reference. This is my capture. Maybe I have more, but now I have just this one. I select it. And you see immediately here I have the measurement result, the solid black line, and the C1 is my reference. Now, red color indicates me that this is a failed. Why? Because my tolerance band has a width of 0 dB, so this cannot be passed as anyway. So what I have to do, I have to increase the width of my tolerance band, just editing it here. Let's go to, let's say, 3 dB. And as long as I'm not talking, you see by the color, green color indicates this is a passed. If necessary, I could even add an offset to move this tolerance band up and down. I don't need it right now. Just mute my EMMA Pro, and so that this way you see it's a very easy way to do this passed-fail test. However, there's one restriction. Maybe you noticed my frequency band, the one that I'm looking at, starts here at 50 Hertz up to 20 kilohertz. The reason is, especially in acoustic setups, the low frequency bands are typically still a little bit unstable. And so what can we do if we need to know more about the low frequencies? Well, the recommendation would be to switch over to the fast pink 4 seconds. And for that reason, I'm going back here to my EMMA Pro. And instead of the fast pink 1, I'm switching to the fast pink 4. And I do the same here on my XL2. Instead of EQ1, I select EQ4. And now after unmuting my EMMA Pro, I need, of course, also to recapture the reference spectrum under the condition of this 5-second fast pink signal. I select memory location 4. Okay. And I select this as my reference. You see, it's much more stable. And now I can increase the width of my acceptance band. So not instead of starting at 50 Hertz as I did before, I could go down, let's say, to 25 Hertz. And by the way, if I would put my hand between the speaker and the microphone, which I will do in a second, then you also see that the result is, of course, immediately a failed. So you have seen it's a very powerful and easy to implement method to not only characterize a device, but also to compare it against another reference for a passed-failed test. So let me get back to my presentation and summarize the prerequisites or the procedure to do this tolerance limit application. The first thing I have to say is when you want to analyze this FastPink 1 or 4 seconds signal with the XL2, you need to have this spectral limits option installed on the device. That's a mandatory prerequisite. Having done that, you can select this measurement function 1/12 octave plus tolerance. Next, you would select the reading, the EQ1 or the EQ4, as you have seen before. You would capture the reference spectrum by clicking on this icon and then confirming with capture. Next, you would select here the start tolerance mode mini entry and select the previously saved capture from the memory, from the onboard memory. If necessary, you can adjust the width of the tolerance band, as you can see here. I also show that to you, and of course also the offset is if necessary. You can, if necessary, adjust or edit the tolerance settings, the tolerance width. You could also say, do you want to have a plus-minus tolerance or just a plus or only a low minus tolerance band? So this is up to you. And having done that, you're ready to execute and run the passed-failed test. Some further comments and hints on this method. First of all, sometimes people ask us, why do we use pink noise? Why don't we use white noise? Just for repetition, to clarify, pink noise, as stated before, is a signal, a random signal with a constant energy content per equidistant logarithmic frequency band. So any third octave or any octave band will have the same energy content in the pink noise. White noise, in contrast, you have constant energy over the linear frequency band. So here we're talking about bands, for instance, from 1 to 2 kilohertz, from 5 to 6, from 10 to 11, or whatever. So as long as the width of your frequency band on the linear scale is the same, you will have the same energy content. But pink noise is more widely spread, is more frequently used because it gets closer to our hearing perception. Our ear is a logarithmically working organ, and I guess you can simply verify that if you listen to a 50 hertz tone and then you increase the frequency one by one, 51, 52, 53 hertz, you will immediately hear the difference. However, when you listen to a 2 kilohertz tone and then you go from 2 kilohertz to 2001, 2002, 2003, you will hardly notice any difference. Only if you go to 2100 maybe or something like that, then you will hear the difference. So our ear is much more sensitive or better able to identify frequency changes in the low frequency band rather in the higher one. And that is just one explanation why pink noise is much more widely spread in the audio world than white noise. The NTA audio FastPink test signal is a periodic pseudo-random noise signal looped seamlessly, so there are no interrupts or edges or something in there. Here we see the time plot of the FastPink 1 signal, 1 second signal. You see it here on the x-axis. It's exactly 1 second, and here this is the time plot of the 4 second of the FastPink 4 signal. For those who are interested, if we would look at the spectrum of these two signals, it is a discrete spectrum. It's not a continuous spectrum. Quite apparently, the resolution of the FastPink 1 spectrum would be 1 hertz, whereas with the FastPink 4 signal, it's 0.25 hertz. This doesn't play really a major role in practice, so you will not notice when working with the signal and analyzing on the third octave band. But I just wanted to show that to you in case that you are interested in a little bit more of the backgrounds of this signal. And if I compare these two signals in practice, I would say the FastPink 1 second signal with 1/3 octave resolution is a nice choice for quick operation and signals roughly 50 hertz or higher. In some applications, you can even go, of course, below 50 hertz, depends strongly on the device you are testing. The FastPink 4, as shown, takes a little bit longer. It offers you typically a higher resolution if necessary, and you can also go typically a little bit lower in the frequency range. Well, that brings me already to the end of my presentation. From my side, I want to thank you very much for your interest. I hope I was able to respond to your questions. And of course, I would be very happy if I can welcome you at one of our future webinars. For the time being, have a good time, stay healthy. Thank you very much, and bye-bye.